Is an associate professor in the engineering physics department. Prior to her appointment, she worked as permanent research scientist at the National Research Council of Italy. She has been visiting scientist at the National Renewable Energy Laboratory and at Purdue University. Her research background is in organic electronics broadly, in design fabrication up to electronic characterization and of organic light-emitting diodes and field effect transistors, material science, nanostructured materials for applications in photoelectrochemical solar energy conversion. And what she will talk to us about today is a very new, exciting direction in bioelectronics. So, thank you, Clara.
Okay, thanks. I think the audio is fine. So, welcome to everybody, and thanks to the organizer for this invitation. It's really an honor for me, and so I hope to do a good job. Okay. So, as Carlos was saying, so what I would like to present you today are kind of preliminary result, I mean 3-4 years, out of a new research effort we are performing in the group, in collaboration with other groups in Quebec, in North America at the international level, on actually the exploration of the potential of Eumelanin materials for bioelectronic applications. So I really have to acknowledge, it's not to be too formal, but I really have to acknowledge at the beginning the effort, the research effort of my students. They are really working hard. They are really working very well. They are really inspiring for me. So Yulia, Vunche, Prajval, Kumar, Jonathan Sayago, and then senior colleagues colleague from École Polytechnique, from the University of Bologna, Napoli, and then UNESP, so San Paolo University at Paura. First of all, not to get scared, but there are molecules. We have to talk about molecules, so we make a shift compared to the previous presentation. And so we have to say that so this eumelanin, it's a natural pigment, so this is what colors our skin, our eyes, our hair. We have it in the inner ear, and we also have in a portion of our brain that is called substantia nigra, essentially because it is colored, and so it contains melanin, actually. The functional properties, the reason why this melanin are there in these 5 organs of senses, essentially, it's really an open debate, and it's there that we try to give an humble contribution as material scientists, as material chemists. We don't want to pretend to be medical doctors, we do not pretend to be dermatologists, we just try to explore the film-forming properties, so the materials property of the eumelanin, and then the charge carrier transport, for sure. So, to give a name to our material, to this pigment, we have, and don't get scared, it can just get worse after. So these are the 2 building blocks. DHI, dihydroxyindole, DHICA, so just the carboxylic form of dihydroxyindole. Now, it looks extravagant, but there are very successful studies, essentially based in Austria, the University of Linz, but several groups, anyway, exploring so the possibility to have indigo-based materials very closely related to these building blocks for organic electronics application. So for application in electronics, in the electronics based on organic conjugated molecules. Even here, we recognize what yesterday, Professor Briseño during the PV conference presented in an excellent manner, pedagogically speaking. So these molecules you can recognize essentially the alternance of double and single bond. So they are conjugated, so we can expect, but then the situation is very complex, a certain electronic transport. Okay, so these are the building blocks of eumelanin, but this is just the beginning of the story. We will see, because these are the building blocks, and then we have to build a material out of these building blocks. What is important is why, Clara, why you put your students on a so complex, extravagant problem? Why melanin? So we said already, for potential bioelectronic application, what is known for the moment is that eumelanin, when it's hydrated is 80–90% of relative humidity, so has a conductivity of about 10 minus 5 Siemens per centimeter. It has a good stability in air and water. It's biocompatible, forgot to add, and biodegradable. But it has, of course, biofunctionality that make this melanin to not to be confused with melamine, nothing to share, essentially. So we have the UV visible absorption, for sure. So melanin protects us, for instance, from the UV solar radiation, transforming the radiation into heat, essentially. It can chelate metal ions, iron, copper, but also less with a kind of lower equilibrium constant, even sodium or calcium, so alkaline elements. And it's also an antioxidant. It also has antioxidant properties. So the first interest from the material science, physics point of view on eumelanin started in the 60s, at the end of the 60s, and somebody kind of claim, if you surf a little bit on the internet, that maybe eumelanin has been the first organic semiconductor to be investigated before the famous polyacetylene that has been reported at the end of the 70s from Eager, Shirakawa, McDiarmid as the first conductive organic polymer. Anyway, so again, if we go on the molecule, we want to give a name to this, a chemical name to this pigment, we can obtain the melanin with different synthetic procedure. And as usual, as it happens in material science, the synthesis of the materials then affect dramatically the functional properties, so the transport, the optical absorption, for instance. So you can have eumelanin by auto-oxidation of DOPA. DOPA, this is the DOPA molecules, the precursor of dopamine, the neurotransmitter dopamine. In the MSO is a solvent, dimethyl sulfoxide. You can have eumelanin by auto-oxidation of DOPA in water, and this is what we could call later, so water melanin. Or we can even obtain the melanin by oxidation of tyrosine. This is the molecule of the tyrosine with hydrogen peroxide, so an oxidizing molecule. This is the synthetic procedure selected by Sigma Aldrich. This is what we used, Julia used most of the time, apart from the cases where we clearly collaborated with chemistry, specialized in the synthesis of the material. So, from a self-assembly point of view, how do we go from the molecule to the material? There are different hypotheses, and this is something that we investigate up to now, but for sure we will have room to work more towards this understanding in the next years. So, I'm sorry. Excuse me. There are hypotheses that say, okay, melanin is a heteropolymer. So you take the building blocks, you connect them in different functional position of the ring, and then you obtain your material. But the leading hypothesis for the moment is that eumelanin results from the pi-pi stacking of oligomer, tetramer obtained out of the building block. The oligomer organized to form what we call protomolecules that have about 1-2 nanometer high, and so the stacking distance is about 0.34, 0.38 nanometer. This is a distance that we also found in our film after, synchrotron characterization. I will not talk about this today, but anyway, this is something that, our results are essentially in agreement. Then a following step where we form, filaments, a small aggregated structure with about 10-20 nanometer high, and finally the material that was functional properties we are investigating actually that forms after this third level of aggregation, and so you have kind of the pile up with 100-200 nanometer high. So as I was saying, surf on the internet, you will find, it's an absolutely fascinating field. I have to be honest, this is really my feeling. So we are in the 70s, Powell, Rosenberg, they claim, look, this melanin, so the melanin transport both type of charge carriers, so ionic and electronic. So the first claim that the charge carriers moving in melanin, in hydrated melanin, is essentially both protonic and electronic, so ionic, and specifically protons, but also electronic, with a ratio of about 2:1. Then we had two science papers, essentially, from Australian research groups. So we are at the beginning of the 70s. McGuinness, Seeley are the corresponding authors. And so the first claim, because of the threshold switching observed in the melanin, so melanin interpreted as an amorphous semiconductor because of this threshold switching in the conductivity detected at a certain, after a certain threshold bias is applied to the material. Then kind of a few years of calm in the field of the research from the material science and physics point of view of the melanin. Up to the moment where, so we had now in recent years, one of the main, the most exciting development of organic electronics is organic bioelectronics, and so at the interface between electronics and biology, so organic materials that you can use as transducer essentially between electronics and biology, and so kind of a revamping in the interest for organic for Eumelanin with the leading group at the University of Queensland in Brisbane, led by Professor Paul Meredith, that has been a great colleague in this for this problem, and so a PNAS paper at the end of 2012 claiming, look, there is in Eumelanin materials a reaction, an equilibrium that is able to explain the possibility for electronic transport to be there, but also protonic, ionic transport to be there. Now, again, don't get scared. We call, this is a redox reaction, so a reaction where electrons are transferred. We call it a comproportionation reaction. And so the comproportionation hypothesis is now the leading hypothesis to explain the possibility of electronic and ionic transport in Eumelanin. And so comproportionation in the sense that the reduced form, the dihydroxindole form, and the oxidized form, the quinone form, of the Eumelanin go towards an intermediate common redox state that is the semiquinone species, so an intrinsic radical species with production of protons. So Paul, I mean with colleagues of course, so they claim we identify the reason why the fact that we can explain the mixed conduction properties of Eumelanin based on what can be defined a water-induced self-doping, so the hydration help, how can I say, to move this equilibrium toward the right, so to produce electronic charge carriers and protons. And so we try to give our, we were very curious, we tried to give our contribution, so we took the most simple, I mean, a very simple experimental configuration to start to explore the charge carrier transport properties in Eumelanin. We selected a thin film form for the materials. Why? Because it's the ideal form to get after, to be applied at the end. We are in an engineering school. I try to not to forget it very strongly. So, we used a very simple experimental configuration, so a planar, a coplanar two-electrode configuration. We deposited our thin film of Eumelanin from this commercial source, so it's actually the sigma Eumelanin produced, so we saw by the hydrogen peroxide oxidation of tyrosine. We had a typical interelectrode distance, in this case, I mean, 10, 20 micrometers is something that you can easily, I mean, achieve in every after every photolithographic process. And so, okay, we try to bias our film and let's see what happens. We want to understand what happens in controlled humidity condition. So the student has a glove box where, differently to what happens all the time, I mean, we are not in dry condition, we do not control oxygen and water, we want to have an excess of water, so 90% of relative humidity, essentially. We kept our voltage very low, so below 1 volt, because we thought to be aware of risk of water electrolysis, but then we obtain results, I mean, completely different from what we expected. Now here it's written gold, platinum, palladium. Come on, it's not a mix of the three, of course, but we used gold, platinum, or palladium, so one color device, but we tried different metals, and we'll see why. So, of course, it's clear before starting to study the charge carrier transport properties, we followed carefully the mechanism of growth of the film. This is one of our expertise in the group. So we tried different melanin different melanin, DMSO melanin, water melanin, tyrosine melanin, so the commercial melanin. We try two different solvents to produce suspension, so an organic polar medium and then also an aqueous basic medium, essentially the only two medium that can dissolve eumelanin. Actually, one of the mysterious side of eumelanin, why it's so difficult to be studied, is that it is essentially insoluble, so it is very difficult to characterize. So anyway, after a few recent reports in the literature, we help ourselves, we are able to engineer thin films sufficiently smooth to be studied for their transport properties. So we observed that we obtain homogeneous, smooth films with DMSO melanin deposited from solution, suspensions essentially, not solution actually, of DMSO. Okay, so these are AFM images, and out of them we extracted we observed the continuity of the film and then the roughness of the surface. We, of course, also try to see, to follow the profile in the film, and actually what we found are, for the surface of the thin film, spin coated from DMSO melanin out of DMSO suspension, we were kind of in agreement with the literature for the step observed in the, along the profile. We also tried, different way to deposit on this, on what remains anyway, a kind of a low surface area. We have a low area. It's a kind of 1 centimeter square, what we cover usually. And so we observed that, for instance, when you drop cast on silicon dioxide or on glass, you can have so different growth mode. You can cover your substrate, but you have an open structure, open structures when you drop cast on silicon dioxide, and so an island formation limited by diffusion. On the other end, when you go with drop cast film on glass, we observe this round shaped island, and so we deduce that the island formation is limited by the sticking to other aggregates. And anyway, we concluded, and this is something that is well accepted at this point, that so the island shape, the aggregate size, depend on the deposition parameter. This is kind of well accepted in general in the field. Now, even we were happy to see at the with the scanning electron microscopy that we have formation of dendrite structure composed of smaller islands, but that we were kind of in agreement with for the surface features that we observed with what is observed for natural melanin. So kind of maybe the studies that we are doing are really helpful after to explore more complex in terms of chemical composition natural system like sepia melanin. Okay, but anyway, let's go back to our story. So we want to understand what happens for the charge transport properties of eumelanin thin films. We applied a relatively low bias, so we were very humble, 0.6 volt, 90% relative humidity, gold electrode, 10 micrometer distance between the electrode, nothing more simple, essentially. But what we observe is after a few minutes of biasing, so there is a first decrease in the current that you kind of could expect, at least if you work in organic electronics, you always expect kind of stress trapping phenomena. But after a little bit less than 1 hour for this specific sample, we observed a jump of about 4th order of magnitude in the current. So this was kind of annoying. We thought about some limitation in the experimental configuration, but it was kind of reproducible. So at the end of the story, we have to associate, we had to accept the idea that these melanin films included between the two gold electrodes is not so innocent at the end of the day. So it's a dynamic system. The hydration and the complex chemical composition that is intrinsic to biomolecular materials made the results really a bit extravagant. So what we observed is at the end, AFM and SEM helped us to deduce that you have the formation of dendrimers connecting the two electrodes. And I make a long story short, it took 2 years to us to understand this result. But anyway, the chloride, so ions present in the precursor materials, because I mean it's a complex material at the beginning. It has biological origin, so we cannot dream about an high purity if you want to use it for biocompatible, biodegradable applications. At least this is what I think. So it has chlorides. It's full of water. The catechol group, this 2OH group in the melanin, are known to have chelating properties, so towards metal. So essentially we were dissolving the electrodes. We were forming nanostructure that at the end connected one side to the other and produced a short circuit that is the reason for the jump we observed. So the first caveat, you want to work in bioelectronics, you like physics, maybe you like engineering physics, maybe you like material science, you have to know something about chemistry, and at the end of the day we will see also electrochemistry. So it's a very complex problem, you want to find very good colleagues, and somehow RQMP, the message is really this one. So, we learned the lesson. We don't want any gold. Gold likes too much our catechol group and our chloride group that are intrinsically present in our material. So we went for platinum electrodes. Platinum is a more stable metal, and so we thought, okay, we solved our problems. And now we study the dependence of the current. So we recorded different transient curves, transient in the sense of current versus time, at different voltage applied between the two electrodes for different relative humidity values. So we observed that there is an hydration dependence in eumelanin. So there is the conductivity is hydration dependence. Okay, we go from 50 to 90% relative humidity. The currents strongly time dependent. We think we have several contributions. So what is this current at this point? Let's imagine if we make the hypothesis that we don't have the solution of an electrode anymore. What is this current, and especially this plateau current that you have after the first decay of the current, probably due to the blocking effect of the ions, of the metal electrodes? Okay, so current is hydration dependent. We knocked on the door of colleagues at the University of Washington in Seattle. So the group of Marco, led by Marco Rolandi. Marco was one of the first one reporting bioprotonic transistor in a Nature Communication of, I think now five years ago. And actually working with him, we discovered, so we used the palladium hydride electrode. If you treat with molecular hydrogen palladium becomes transparent to protons. So you can really measure protonic current, and we proved measuring at different relative humidity our sample before activation of the palladium, so in dry nitrogen atmosphere, in nitrogen atmosphere, or after treatment of the palladium with molecular hydrogen, we actually proved the fact that protonic currents are there, and we cannot completely exclude, of course, the presence of other ions, especially after this advanced functional material work, but we were able, for the first time, to clearly measure protonic current in eumelanin. So ions move in melanin. This is kind of the first time that in thin films this measurement, this conclusion has been obtained. Now, what about the electronic transport? This is a very delicate story. We said, okay, now we can quantify the protonic transport. We could subtract the current, the ionic component to the current that we measure into electrode configuration. Things are not so trivial at all. So, and again, I think it's kind of a caveat for people that want to work in this interfaces field where really electronic meets biology. Let's take care of the basics of electrochemistry. I think this is my very humble message. At least this is the lesson we learned. So what do you observe? You observe if you run current versus voltage experiments in a very simple two-electrode configuration. If you keep the voltage extremely low, let's say comprised between 0.2 minus 0.2 volt, okay, the current are what we could call kind of innocent. So it's a capacitive current, so in agreement with a quasi-linear dependence on the sweep rate. Here I have 4 different curves from 0.5 millivolt per second to 500 millivolt per second. But as early as you start to increase a little bit the voltage, keeping Anyway, the interval, the applied electrical bias well below the water electrolysis threshold, that is, this 1 and something volt, you start to have quasi-exponential dependence on the voltage, so a kind of non-capacitive behavior. In other words, electrochemistry is there, okay? So these curves run between 0.8 volt in these two electrode configuration, 90% of relative humidity, that show that cycle after cycle your current is decreasing, indicates, in my opinion, very clearly that you have irreversible oxidative behavior in your material. And actually, when we run so transient measurements, so current versus time, we also observe with the AFM a change in the eyes of the material deposited on the two electrodes. So somehow mass transfer is also enabled in our not just charge transport but also mass transport, we think happens in our film. So it's really a dynamic system that we have to with a complexity that we have to accept if you want to investigate it. So there is a kind of a permanent reduction of film thickness, for instance, after biasing at just 0.5 volt, a proof of the irreversibility of the dynamic, I would say, more than the irreversibility of the problem. We recently started an electrochemical, a cyclic voltammetry survey, more complex again of what we were expecting. Anyway, so Prashval was the student in charge for this project. And so again, what we observe, running an experiment with sigma melanin films deposited on indium tin oxide conductive substrate using a typical three electrochemical cell with platinum counter electrode, saturated calomel electrode as the reference, removing the oxygen, of course, from our system, being a pH 7.4 because of a phosphate buffer, and going at a sweep rate of 50 millivolt per second. So we observe a first peak, a first oxidative peak, very intense, broad and intense, that again, in our opinion, point to the possibility to have irreversible process, and so not just a charge carrier transport in our film. So this peak, as I was saying, as the irreversible, interpreted in terms of irreversible oxidative peak, attributable to kind of polymerization processes involving oxidized species in our film. So close to the positively biased electrode, we produce this oxidized species, so we can go up to the quinone, and then we can also oxidize other functions in the building block, and then these reactive species are responsible for a polymerization process. So let's wrap up. Just to give you a message now, out of all these results, we have proton transport. The current is humidity dependent, time dependent. We have proton transport. So what? What is the state of the art, at least to our knowledge, in terms of electronic transport in Eumelanin thin films? We have to keep in mind the redox, the possible redox reaction, as I was saying, from the hydroquinone, semiquinone, quinone form, with the possible tautomerization as a function of the pH for our quinone form. We have to keep in mind this Paul Meredith, Bernardus Mostert hypothesis of comproportionation reaction. The name is kind of not nice to pronounce, but anyway, it's a relatively simple concept. And out of this, we're kind of proposing now our model. That is kind of the take-home message even for my presentation today. So we try to model, and Julia had absolutely a leading role in the formulation of this hypothesis. In this model, so initially we have, this is kind of as a function of the time of biasing, A, B, C, three different steps as a function of the biasing time. So initially we have, semiquinone, quinone, hydroquinone, the three redox species of the building blocks constituting the melanin. There are dissociated protons, for instance, because of this carboxylic group present in the building block. So we have a certain composition before biasing. Under electrical bias, for sure, so proton migrates, they affect the position of the comproportionation equilibrium just because of the Le Chatelier principle, okay? So where we have more protons, we go towards the left in the equilibrium, more protons we go toward, less protons we go towards the right, okay? And following this, we start at a certain point to have electron transfer at the electrodes. And so the point is that if we have this electron transfer, at a certain point we achieve the maximum oxidation state or the maximum reduction state for our melanin. This means that kind of we make at least one of the two interface insulating, and so kind of we could explain the difficulty in identifying this electronic transport just because at a certain point at least one of the two interfaces is become insulating because of these redox processes taking place. So proton migration and full reduction of eumelanin close to the electrodes might hinder a sustainable electronic current. So I would pay attention to the words that we are using. Of course, this depends on the interelectrode distance that we are using. This depends. This is a function of the time, so we don't say that it's not possible to have electronic transport. We just kind of propose our experimental result to say why it has been so cumbersome, why it's 50, 60 years that people say, okay, it has a conjugated structure, these materials, but I'm not able to detect any electronic current. And it's a pity because I could apply these melanin thin films in sensing devices, for instance. So we think that redox processes at the interface are contributing to hinder this, what I like to insist on these adjectives, a sustainable electronic current with this specific experimental configuration. So, if I have to try to draw a conclusion, and I like the expression that yesterday Dr. Petrozza used, it's kind of a steep learning curve. So at the end, it's still absolutely a learning curve. Anyway, what we learned is that the response of hydrated eumelanin thin films to electrical bias is complex. This is as diplomatic as possible, we can call it complex. The electrical current is hydration dependent. Eumelanin thin films are proton conductive. This is the experiment with the palladium hydride electrodes. There are, of course, other ions in our film, as this dendrimer experiment demonstrated. So we have dendrite growth and resistive change of eumelanin films between gold electrodes. We have several indications for other electrochemical reaction at low voltages and possibly weak electronic conduction. At this point, we know that we have to draw, like this study is almost concluded, and so next Tuesday this will be kind of submitted. It's a huge work that we will submit as soon as possible. We will have, of course, other two projects, so one really electrochemistry oriented, the other one self-assembly oriented along the same streamline we discussed today. So now point is, so strategies, apart from these fundamental studies, of course we want to enhance this electronic transport because we would like to use eumelanin in transistor for sensing applications. So we have to find a strategy essentially to enable the transport and then to dope the material, and to have a clear fundamental understanding of what is going on in the material. We have to go for unconventional microfabrication patterning techniques. We don't want to have melanin everywhere, giving us a huge capacity of components to our current. We really want to clean up, to have just the materials between the two electrodes under investigation. Okay, thanks a lot for your attention. I take your questions.
Thank you very much, Clara. Are there any questions? Don't be shy. I was going to ask a question about this very last slide that you showed, where you were talking about enhancing electronics transport in order to then be able to use this for certain applications, particularly in sensing.
Yeah.
With such a complex electrochemistry going on, how does one envision the sensing application working? Is it particularly the the molecule that is going to be then reacting selectively electrochemically, that will then you will then detect changes in the ion transport.
Yeah,
Is
yeah.
that
I
the
think we
assurance?
cannot. It would be kind of misleading. It would be not appropriate for me to give a clear answer before having cyclic voltammetry runs in completely so in a systematic manner. We just have in mind if because this electronic transport in principle has to be there, maybe on length distances or nanometric distances instead of micrometric distances because of the heteropolymer character of the material. But anyway, the ability of melanin to chelate, as I was saying, I mean, copper, iron is so important, even for instance, in the prevention of the Parkinson diseases, that I think it deserves, and in engineering studies of the material, close to what Alberto Saleo just demonstrated in his Nature Materials 2013. Yeah.
Thank you. There's a question over here.
Yeah. Sorry, the end of the question I missed. Yeah. Look, I think we have to be very open-minded in the sense that this field of organic bioelectronics is really booming. People are showing gating with water of classical organic semiconductors. It's also very delicate for me. I have 3 glove boxes perfectly connected in my lab. I check the ppm every morning. But so I think we have to be, there are materials that can really work, I mean, in aqueous medium. So let's not be too exclusive. You really have to give a chance. And anyway, look, these materials in nature is full of proteins all around. It's of course, I mean, it's in our body, huh? So you cannot be so scared of water, in my opinion.
I think there was one more question here, or no?
Yeah.
Or,
Yeah, there is nothing that is silly. Huh? So, again...
so the question was, is there a connection between what these materials do physiologically versus here in this device?
Yeah. Look, what I think now, I have to be honest. If I think that this Eumelanin now entered in my life and will not live very soon, so I think for 10, 20 years I will keep studying this material, is because really the fact that it's in all the senses, I mean, it's in our skin, it's in our eyes, it's in our air, so we make all kind of functional property hypotheses for the moment, but these are just very preliminary hypotheses. For me it would be a lot just to study at a certain point in a few years the sensing, how you chelate the ions. This could really help us to understand how to limit at least neurodegenerative processes, because if we keep these toxic ions in the melanin network, so this could already be a lot from, by my point of view. It's a kind of an international effort to arrive at the point that you are kind of imaging, I think. I really have to be honest at this point.
Okay, I suggest that we move on. We're running exactly 15 minutes behind. Now is the coffee break.